All right, may I have attention, please? So let's start today's lecture. So the part 2 is about how do we design a controller to improve the performance of the system. But system we want to control, and there is something that we want to focus on. We want to change, so we measure this output. We compare with the desired output. And the objective of the controller is to minimize the difference between the desired output and the actual output. So feedback, that's the fundamental principle for controller design. We'll try to make this output, this actual output follow the desired one. So we call feedback because you have to use a sensor to measure the output. Okay, last week, we introduced the first type of controller, the pole placement. Now to design this pole placement controller, we have to know where are the desired poles, right? So how do we design the desired poles? How do you design the desired poles? That will come from the performance requirements, right? You cannot say the desired poles are given by me when you go out, right? The desired poles will not be given by your boss. So there are certain performance requirements for the system to satisfy. From those requirements, you design a reference model which can meet all the requirements. So the poles of the reference model will provide kind of a desired poles for the closed loop. Now, just remember, can you recall what is the key step to obtain the solution to the pole placement problem? So what was the trick? What was the key knowledge we have used to get the solution? The kinetic form, right? The kinetic form. Controllable kinetic form, right? So that's how we get the solution for the single input, single output system. That is also how we get the solution for the multiple input, multiple output. But for the single input case, there is only one controllable kinetic form. Okay, for multiple input case, right? There may be multiple ways to design the desired controllable kinetic form. They will share the same poles. Okay, so that is the reason that for the single input case, you only have one solution, but for multiple input case, you may have a multiple solution. Now, how many reference models can you build to meet the performance requirements? Is there only one reference model to meet the performance requirements, or there may be possible models? Or is the solution unique, or there may be multiple models? That should be an easy answer, right? Tell me. There are multiple ways, right? Because those requirements also, you will put in the way that, okay, the overshooting is less than something, right? The settling time has to be less than something. They are all given in terms of inequality. Any number satisfies the inequality. Of course, there are many ways to do it. So the many reference models can be built to meet the performance requirements. Then you may wonder among all the models, right? Could be one of them would be the multiple one. And how do we find out the best one? That may not be easy, right? It will depend upon the criterion for best. Okay, so then that is actually a problem of when we talk about the best, when we say it's a problem of about optimization. We want to find out the best. And we know that the control specifications often may have a multiple objective which can conflict with each other. For example, if you want to reduce the steady-state error, if you just use a simple proportional control, normally it means that you have to increase the gain, right? But if you increase the gain, it means you have to apply a bigger value of the input. That means that you consume more energy. It is more expensive. So this is just a simple illustration of about the effect of how do you achieve the best trade-off or compromise between the speed and the cost. Now, normally we say if we look at the control effort, or okay, this is the minimum time, right? It says if you want to be very fast, right, your control effort. Okay. This is drawn here by this blue line, right? Means that you have a big control effort, which means you have to be more expensive, right? And then, of course, you say, I want to save, right? I want to be save the energy. I want to save the cost. Then you say, okay. Then you on this end, if the control effort is small, but meanwhile, which means that the speed of your system, right, will be very slow. Okay. It's like, if you buy a car, right? If you buy a racing car like a Ferrari and a normal car, right? Which one is cheaper but can be much faster? So therefore, of course, for it depends upon which way you want to go, right? It depends upon the objective, and also depends upon your budget. So therefore, in the reality, we want to achieve a trade-off. Then when we talk about the best, we have to specify something wrong. How do we measure that? Then that go into that is the subject of the optimal control problem, right? Where we want to control our system, and we specify, right, those performance requirements into a set of cost function. Okay, there is we'll call the index function or cost function, and then the control is going to minimize this cost. Those cost functions, there are many examples, like you probably want to be very fast, so you want to find out the system which is with the fastest speed, so minimum time, or you want to save the energy as much as possible. You want the minimum energy, okay? And of course, in reality, normally we want to achieve the balance between those two, right? The speed and the energy. This is what we call the linear quadratic regulator. Okay. Then for control system design, many will focus on the third one. So this will be the main topic today, the linear quadratic regulator. Okay, let's formulate the problem mathematically. So what is LQR? Now you can say, okay, of course we use this ABC, or now you are all familiar with the standard form of a state space model. The objective is to try to bring the state from a non-zero initial state. Okay, you see the initial state is not zero. Okay, we want to bring the initial state to zero. Of course, we know when x equals 0, that is the equilibrium point, right? We want to bring the state from non-zero to 0. The equilibrium point, this is called the regulation problem or the stabilization problem. But of course, you see there are many types of a stabilizer to make it work, right? So then we want to pick the best. So we say, okay, among all of the stabilizer, we want to minimize a quadratic cost function. Okay. So here we say, okay, this is the mathematical form of the cost function. Because there are many inputs, so x is the vector. Also, the input may also be multiple inputs. That's why right here we use this is what we call the quadratic form. Quadratic form, right, is the transpose of vector times symmetric matrix times x, and this here is this R is also our matrix. In this way, right, we specify the cost function. So we sum them up, right? Integrating means summation. Of course, if we want to minimize this, eventually the x has to go to 0, right? If x goes to some non-zero value, you integrate, sum them up, it will blow up, right? It will go to infinity. X will go to 0, then we say, okay, how fast we want to x go to 0 and how much? So here is the term which will penalize the input signal. If the input is big, right, then this cost function may also be big. Okay, then we say, given a Q and R, we'll try to find out a control law that will minimize this cost function. Okay, later we're going to show that the mathematical form of this control law will be like this. So the input U equals minus K times X. You just look at this form. Is this the controller in the same mathematical form as that for the power placement controller? Look at this form. Yes or no? Yes, right? It's just a kind of a proportional control, right? In some sense, it's just like gain matrix times the state vector. Of course, the only difference will be, right? The only difference will be how we're going to compute this gain matrix. Okay. Of course, you may ask, why the optimal control, right? The controller which will solve this, minimize this cost function, has to be in this form. Can we use some other kind of forms, like a nonlinear controller? Will nonlinear controller be better than this linear controller to minimize this? So later today we're going to prove that this is the only way. This is the only solution to minimize this cost function. Okay, so later we're going to prove that. So, all right. Now, so you may wonder, right, in this form, what is Q and R? We're talking about a quadratic form. So if you learn something about the linear algebra, you may still remember something about the terms, right? What are the individual terms of those forms? Okay, normally you design those Q and R, right, are in diagonal form, because if you are diagonal, that will make the physical interpretation of this form much easier. In addition, right, we are going to explain that Q should be semi-positive definite. If Q is in a diagonal form, semi-positive definite means that all the diagonal terms, right, has to be non-negative. Could be 0, but cannot be negative. That is the requirement for Q. Then we also require the R, but R will have a strict requirement, says that R has to be positive definite, which means all the diagonal terms are all positive. Or in other words, right, R has to be non-singular. Okay. Now, with this in mind, right, if Q and R are the diagonal matrix, right? Then we express out, we write out the expression of this quadratic form, just means this one. The X transpose times QX is just the combination of those X squares. Then those Q, those are just the weights. Okay. Then we say those Q, of course, we look at that are relative weighting among the state variables. If Q1 is bigger than Q2, okay, for example, right, we say we put there are two state variables, is Q1 is 10, Q2 is 1, which means we put more weight, right, more emphasis on the first state variable. Finally, you can say that if xy equals 1, right, in this cost function, it becomes what? Multiplied by 10. X2 equals 1, it is still 1. So, which means you want to make those x1 much smaller than x2, right? Because it has more impact on the total cost. Okay? So there is the higher penalty price on the error x1, right? And the control will try to make smaller x1 than x2. But of course, eventually, all of them will go to 0, right? Like I said, eventually all the state variables have to go to 0. Otherwise, right? Otherwise, the cost function will blow up. You sum up because the integration is from 0 to infinity. Okay, and then if we look at the other terms, the quadratic form, the U transpose RU is just a combination of the square of this input signals, and those R are relative weighting among those input signals. If one control input is more expensive to implement than another one, then of course we put a higher weight on that. We try to minimize that, right? So then that input will be smaller. The value of that input will be smaller than the other inputs if we put a higher weight on that. Okay, and then later, right? Later, we may want to express those Q in terms of in this way. Okay, it is easy to say if Q is a diagonal matrix, right? This H is just the square root of this Q. So you just take the square root of all the diagonal values, you get this H. Right? But of course, you may ask why we want to do that, right? We want to do this just in order to prove the stability later. Okay. This just for your information at this moment, we want to express Q as a square of our matrix. Okay, to understand the whole idea of those linear quadratic regulator, let's take a look at our one simple example. It's just a first order system, right? The state is a scalar. The input, there is only one input. Okay, and then of course we want to bring those X state from a non-zero initial state to 0, right? With a simple state feedback. So this input is just minus k times x. K is a scalar. So we want to find out what is the best way to do it. But first, to look at this system, is the open loop stable? Clearly, right? Clearly, the eigenvalue is 1, right? Positive. So it is not stable. If we don't use feedback, the state will blow up, right? Okay. So that's why we need a feedback control. Then let's plug in this feedback into the system, right? Then we get a closed loop described by this equation. So what is the condition on this gain k such that x will go to 0? K has to be less than or bigger than 1, has to be bigger than 1. So somehow I think somebody called 1. I don't understand why you think the answer should be 1. If 1, right, x dot equals 0. That x dot equals 0 means that x will keep as a constant, right? You want to make it stable, so you want x go to 0. So ending k bigger than 1 can do it. Of course, we want to know, okay, what is the best? So then we say we have to know what do we mean by best, okay? If we are mainly concerned with the speed, we know, of course, the larger k, right, the faster the speed, the faster the x will go to 0. But how, on the other hand, we know if we put if you look at the expression, right, a larger k means a larger input signal, right? So means a higher amount of control efforts, which is a higher cost of the energy. Okay, so then on the other hand, we say we do not wish to apply any more control effort than is necessary. For example, right, we wish to use as little power as possible. So on the other end, then we should keep U as small as possible. So we want to keep this K very close to 1 if we want to save energy. Okay? But in reality, right, we want to keep a compromise or trade-off between the speed and the cost. So that's why we want to say, okay, now we want to something in the middle. So we want to minimize the following index. That's why we want to design a cost function. In this way, we say, okay, I put some weight on the state. I put some weight on the input. Okay, so that's the meaning of Q and R. The weights for the state and the weights for the input, and then we want to minimize that. And you will notice I put a 1 over 2. Of course, this one just introduced for some theoretical communities. Then those Q and R express the relative importance of keeping x and u near 0, right? So if you want to put more emphasis on x, we will put higher weight q. In this case, right, if q is higher than this x, will convert to 0 faster. But on the other hand, the control effort will be bigger, will be more expensive. Okay. If we care more about the energy cost rather than this response speed, then we may want to set a higher value of R. Okay. Now, then although we want to minimize this cost function, but the final value of this cost, right, that is not our objective. We want to minimize this to derive the control law. Okay, so the numerical value, right, of this J is not important. That's why I would say, of course, you want to say, I want to minimize this J is also equivalent to minimize without those 1 over 2. And also you say the Q and R, we can just set one of them as 1, right? Because it's just relative importance that matters. Okay, so this one, so why the controller has to be in this form, we're going to show that later, but for the time being, we just assume, okay, we're going to use a linear feedback control. And we want to minimize, so now we set R equals 1. We want to reduce the design variables because I only have 2, right? Those Q, right? Then because we say it's just in the relative importance that matters, right? So we can rewrite our cost function this way. That will simplify the calculation. And then we just plug in expression of this input. Then easily we have this expression for the cost function. We can't get this one because we know U equals minus K times X. Okay? Any questions? Okay, then we want to find out the best value of k, right? The best value of k to minimize this cost function. So how are we going to do that? From calculus, we know that if we want to find out a minimum of a function with one variable, right? Here k, of course, is just a scalar variable. One variable. What should we do? Derivative equals 0. So you see this is easy, right? Since you have learned the calculus. Okay. Okay. In this way, so therefore, we are going to compute the derivative of this cost function with respect to the gain k, right? Okay, let's just go ahead and do that. Okay, so this is the expression of this cost function in terms of k. Then let's just do the derivative. Okay, if we do the derivative of k squared, of course, that becomes 2k. 2 cancel out, we have this k. Q is a constant. Then we get k equals 0. Then the input equals 0. Is this correct? So something must be wrong with this whole procedure. So which step? Did I make a mistake? What was wrong? What? When x equals 0, k can be any value. X will not be 0, right? We know x0 is not 0. Yes, exactly, right? We won't do that. X actually is also a function of k. X depends upon the state variable, depends upon the control law, right? So in order to do that, actually, we need to first get the solution of this x. That is the most difficult part for the linear quadratic regulator. But for this scalar case, we have a simple solution because we know, okay, this one, because it's a first order system, to plug in the controller, we have this closed loop system, right? And then this one, right, you know, the solution is e to the minus k minus 1t. You can say the x depends upon k. And then we compute the integral, right? We plug in, we get the integral. And finally, okay, I'm going to skip how we compute the integral. Assume that everybody can do that. It's just an exponential function. Okay, you do the integral, and then we get this one. But finally, this one we know, okay, obviously j is a function of k, right? K and x0 is a constant. Now we can compute the derivative. Okay? Then we get the derivative. So I also skip the details of how to get the derivative. Okay, you are the graduate student, everybody should know how to do that. Then this is the equation for the when the derivative equals 0. There is a quadratic equation of two solutions, k1 and k2. So which one should we pick? K1 or K2? Of course, it has to be K1. We know K1 has to be bigger than 1, right? To assure the system is stable, so we only pick K1. So that will be the final solution. So we say this is the optimal solution, then we get K. And this one will optimize the cost function. Okay, now you can say this gain, of course, will depend upon the weight factor Q, right? We say that Q actually is the weight for the state. We put a higher Q, we put more emphasis on the state. We want it to be much faster. You can say also means, right, we'll have a higher value of Q that will give us a higher gain, right? The higher gain will get a higher control signal. A higher value control signal means that it will be more expensive. However, right, we see because this 1K is again a much bigger K will give you a larger value of U. Then of course we'll only have a smaller Q. Then we'll have a smaller K. The parameter is select to achieve a compromise between those efforts. Later we're going to discuss more on how do we design those Q. Now, here I will give you again, I just give you some real-world applications for when the AirQR can be used. So here is a pitch controller for aircraft. So I guess everybody in this room have experience, right? Taking the flight, and then if somebody sit on the seat close to the window, you may notice how the control surface on the wings they move. But here is a close-up on how this control surfaces on every side. Without the aileron. Without the air brake. Okay. So for this problem, we will try to control the pitch, right? This way up and down. And how do we control that? Of course, in that video clip, you already know that there are elevators at the end of the airplane. The elevators, when they move, right, they will make this plane up and down, the pitch. Okay, then so I will skip the details of the model. So in this case, so we say the pitch will be controlled by the elevator. So delta will be the elevator deflection angle. So finally, we can have a third order system. So alpha, q, theta are the three state variables. Delta are the elevator deflection angle. Because theta is the pitch angle. So in terms of our standard state space model, this is A, this is B, this is C, right? What is the design requirements? So we want the rise time for step response. We want the rise time to be less than 2 seconds. Right? The overshoot, we want to be less than 10%. The 2% settling time, we want it to be less than 10 seconds. Okay, so those are the performance requirements. And you know, if you follow the power placement controller, you are going to use those one to design the desired values of the poles, right? But here, so today we're going to learn how to solve it using the LQR. So we don't have to design the desired poles. But before we design the controller, let's see what happens if we don't use any feedback control. What is the step response of the open loop? So if we apply just a constant deflection of the elevator, this will be the pitch angle. So it just increase like that. This is the step response. If you look at this step response, then you will realize, is it stable or unstable? For a stable system, we know that the step response will settle down to some constant value. Definitely this is unstable, right? So the open loop response does not satisfy the requirement. We have to use feedback. Okay. So we will come back to this design example to see how we're going to achieve the performance requirement, right? But first, let's try to derive the solution for the LQR. Okay, that will be the main subject for today. So how do we solve the LQR problem? First, we need to answer, right? Can we solve it? So what are the conditions? Okay, so we need some conditions, definitely. And then we'll try to get the solution. Okay, to understand those conditions, I just give you some of the examples for you to have a clear idea about all those conditions involved. First, look at this example. X1 dot equals X1, X2 dot equals X2 plus U. And then we have this performance index. Q equals 1, right? This U, only one input, U equal R equals 1. Does the solution exist? Okay, let's just get you a more clear idea about how this state variables. This is X1. This is X2. From this equation, we can X1 will be affected by itself. X2 will be affected by X2. X2 will be affected by the input. Right? If we use our graph to show the relation between the state and the input, do you see some problem? Uncontrollable, right? Whatever you apply the input, x1 is not affected, right? And then you say the equation for this x1 is it stable or unstable? Unstable, so x1 will blow up, right? X1 will blow up. Therefore, x1 will blow up, right? So therefore, this cost will blow up. It does not have a minimum value, right? Is that clear? Okay, so the reason is simple. There's no minimum for J because x1 is uncontrollable, and whatever you do with the input, right, does not affect the x1. Therefore, this cost will blow up. So from this example, you can say, hey, the control system has to be right stabilized. So therefore, we know that for the pole placement problem, we know how do we place those poles. We have a solution. There is a condition. The system has to be controllable, right? State variables can be affected by the input. Then from this example, we say because there is no solution because the x1 is uncontrollable, and also this x1 is also unstable. Okay, that causes us the problem. Therefore, we make the following assumption: the system is controllable. Do we have the same requirement for the solution to pole placement problem? Right, has to be controllable. Okay. Now, then we know that if the system is controllable, we can make it stable, right? So, but for LQR, uncontrollable is not enough. Also, when we design your cost function, we have to put it in a proper form. The choice of the performance index or the mathematical form of the performance has to be carefully chosen. Okay, to see that point, now let's look at this example. Still is a scalar example. X star equals x plus u. Now, if I put the performance index in this way, what is the input to minimize this cost function? 0, of course, right? You have put u equals 0. But we know if u equals 0, what will be the x? X will blow up because it's unstable, right? This is not what you want. Okay, you have something to minimize the cost function, but the system becomes unstable. That is not what you want. So to make sure that the system is stable, we needed the performance. You see, the problem with this performance index is does not contain any signal related to the state variable, right? So the performance index has to contain some information about the state. Okay? That comes to the second assumption. We say the pair, we put this condition. So we pair H is completely observable. So H is a matrix that satisfy this equation, right? It's kind of H is a square root of Q. So later we are going to explain, right? But why we put it in this form? We will try to prove the stability, but roughly speaking, right now we say, okay, it just means this performance index has to include some state variables, and not necessarily we don't have to include all of them, but let's say if we include some of them, if those state variables behave properly, then we know, because the state variables are related to each other, okay, in some sense, and that will those state part of the state variables behave properly, go to 0, or the other state variables will also go to 0. Okay, that is the second condition, say that the performance index has to include some state variables. Okay, now then the algorithm we're going to develop will be stabilized, right? Stabilize any mode that is controllable and that appears in the performance index. But also we want to make sure that the control signal itself has to be finite or implementable, right? If you end up with some controller which requires an infinite value of the input, we know it will not work. So that comes to the third assumption about the value of Q and R. So we require this weight matrices, right? Those Q and R, they are symmetric matrix, and we require this Q to be semi-positive definite and the R to be positive definite. So this one, we apply this assumption, just make sure that the cost function does has a minimum, right? For example, if we don't do that, if we put some negative sign in this cost function, right, we know it may be made as negative as one wishes when the input go to infinity. Right here, you look at this one, you want to minimize this, of course, we want to, it does not have a minimum value. If I put this U go to infinity right here, the same is true for this one. If I put X go to infinity, this also, this J will go to minus infinity. That's not what we want. We want to have that minimum value. So that's why we want this whole term inside this integral, we want to be positive. If we want positive, we know at least, right, it cannot be smaller than 0, right? So we know it has some minimum value. The cost function has to be bigger or equal to 0. Okay, so that's why we'll put the Q and R to be positive. Finally, let's talk about this condition. We require this R to be positive definite. Okay, again, let's just look at a very simple example here. This is a system. Of course, this system is stable, right? Because here we have a minus X. This cost function, we know this Q is 1, but R is 0. Well, R is 0, we say, right, we say that R is semi-positive definite, right? Because R is 0. If we want to require R to be positive definite, R has to be bigger than 0. Here we want to show why R cannot be 0, okay? Now, if you just look at this problem, so R equals 0, so R is semi-positive. If you want to minimize this, what would happen in this case? What would be the, if we minimize this cost, and then we get our controller, what would be the control gain? The gain will be infinity, right? If I have a gain equals infinity, actually I can make this J to be very, very small, right? Very, very small, okay? So it is unacceptable if we this way, if we solve this one up, the K will go to infinity. But K go to infinity means, right, the input will be infinity. If you have that power, right, you can make this X go to 0 very fast. How fast? The T can also go to 0 immediately at one instant. But we know it cannot happen, right? K cannot go to infinity. But the problem with this solution is because we didn't design our cost function properly. we have to include those input into the performance index. Okay? So in summary, the assumptions 1 and 2 guarantee that the optimal control system is stable, and the assumption 3, others R is bigger than 0, ensures that the control input is bounded for physical implementation. Okay? Any questions so far about the assumption? Okay, now let's move on to talk about the solution, right? So here is the problem. So this is a system described by this ABC, which you are all familiar with. And we want to minimize this cost function with Q positive semi-definite, R is positive definite. We want to find out a state feedback control law, right? In this form, U equals minus KX. Remember, we're talking about the multiple input case. So X is a vector, the input U is also a vector, right? K is a matrix. So how are we going to do that? Then you recall what we did for the scalar case, right? So you say, hey, we solved the scalar case. Why don't we follow the same procedure? So let's plug in the control law. We know this U equals minus KX, right? We just plug it in. So A minus BKX. You know, from the part 1, you know, this is the solution, right? This is the solution. So you say, hey, I know the solution. So let's just evaluate the cost. So let's just plug it in, right? U here, and then equals minus. Okay. I guess there may be some typo here. This should be minus. Sorry, no, there's no minus because there is a minus K, there is another minus K, so it's plus. We have it here, but then we plug in the expression of those X. So let's plug it in. This, and then you look at the expression of this. Remember that this A, E, K, they are all matrix, right? It involves the matrix exponential. We know that if there is only one, it may be possible to get the integral, right? We know its derivative of a matrix exponential. That is fine. But unfortunately, there is another one, right? There we have two of them. How are we going to compute the integral? It's not obvious how we're going to evaluate this integral. Okay? So we cannot follow that same idea. So the solution to this AQR is not as simple as the power placement problem. For power placement, I would say it is straightforward, right? Once you know, apply the idea of the controllable canonical form. Just try to match those two controllable canonical forms, right? You compare, then you get the solution. But here we say, okay, even if we want to get the derivative, we know we cannot compute the derivative. Well, but how do we get the solution for some minimization problem? Computing the derivative, that's the most commonly used technique we have learned in calculus. But that doesn't work, right? So we have to try to find out the solution from another perspective, okay? Well, just to motivate you to think about the other way, so let's still try to find out a solution for the scalar case again, but this time we're not going to directly use the way of differentiation, right? Because we know that method cannot be extended to the general case. We want to find out another way, okay? So let's look at this example again. A scalar case, Now we put this A and B because later we keep in mind, later we're going to have A and B again, but it's capital A and capital B, right? A matrix A and matrix B. So here A and B just of course are scalars. Fine. The index we say Q and R. Okay, we put those both Q and R in the performance index. In this case, of course, Q and R are only scalars. So okay. So this time we are going to try the near-prof method. Then we define our near-prof function, right? And then you learn the near-prof function in part 1. So we put this V, right, equals P times X squared. And we know, of course, P has to be positive. But which P are we going to use? Actually, that was the key. So we say, we know it is positive. We want to design it later. Then we say, okay, near-prof method means, of course, the important thing is derivative, right? Let's compute the derivative with respect to time. dv dt, right? This is 2p x dot, right? And then you plug in the expression of x dot is ax plus bu. Then we get this expression for this derivative. It contains x and u. Okay, from part 1, you say, okay, to assure the stability, what is the condition on the change rate of the near-prof function? What is the condition? It has to be come on, that should be very simple. Tell me, what is the condition? You have learned that, right? Don't you? In part 1, what is the condition on the change rate of the near-prof function? Has to be negative, right? Have you learned that? In part 1. Is it covered in part 1? Another one, nobody answered me. You all forgot? Or? Okay. We want to find out P and U to make this happen, right? We want to design P and U to make this change rate to be non-negative, non-positive, sorry. Okay, so what is the next step? Okay, then we say how are we going to relate this near-prof method with the minimization problem. So somehow we have to relate this near-prof function with the cost function J. So if we can relate the change rate of this near-prof function with the qx squared and ru squared, which is the integrand of the integral for the cost function, then we can connect the cost function to the near-prof function. Okay. So here let's just write down the expression of this change rate of the near-prof function and the integrand of the cost function, right? Qx plus ru squared. Then you can say, how do we relate those two? As it appears, right, the mathematical form of those two are very different, right? So you say, how are we going to relate those two? Of course, the idea is not obvious, right? It is not obvious. So that's a very important step in the whole solution is, okay, I want to relate those two. Let's just force them together, right? Okay, they are not, they don't like each other, right? Now not the same. They're not in any way similar to each other, but let's put them together. It means, right, this is the change rate of V. Okay, I want to relate to Qx and Qx squared plus RU squared, just plus RU squared plus Qx squared. Of course, I have to minus Qx squared minus RU squared. Okay, of course, you say mathematically say, so why are we doing this, right? Plus something minus something. Okay, but that is the way how it will work out. Okay, so let's just do this, and then we just now we can analyze the expression of this change rate of this BR4 function. We know the purpose is that we try to design this P and U such that, right, this change rate will be non-positive. Okay. Then you look at this form. We already noticed, of course, we know that Q and R are positive. So those two terms are non-positive, right? Negative sign. That's what we want. But somehow those terms, we're not sure, of course. We know P is positive, but A, of course, depends upon A. A, we don't have any condition on A. A could be positive or negative, right? That's X squared. This RU squared, Q, X squared, those are positive. But those X times U, that is the most difficult term. X times U, we don't know it's positive or negative. Okay? So, but we know the final two terms, they are negative. That's what we want. If we keep it there, then how about the other four terms? That's the terms we want to cope with. Those four terms. Okay? Because those two are negative. That's what we want. Then we ask the question, can we design? Remember, we can choose the P, right? We can design the control input U such that those four terms can be zero. If that is possible, right? If that's possible, actually we achieve if this can be done, right? We can make this one to be less than or equal to zero. This is zero, we are left with minus Qx squared minus RU squared, right? Okay, now, then in order to deal with this, because we know, okay, how we're going to do that, this X times U, we know X times U, right? It's very hard to decide it's positive or negative. Okay, but we want to put it into another form, into a form of something, of a square of something. Then that's what we call a completed square. Okay, let's just complete the square for this term. Now we know here is X times U, right? We already have a U square. We need a term on X squared. Okay, let's make it more clear to you. Let's just focus on those two terms. Let's put our 1 over R on outside. Just make it clear to you then. So because I have 1 over R, so I have this 2 times 2 PB RXU, right? Then I put R squared U squared. That takes care of those two terms. I still have those 2 PAX squared. I put it here. I have this QX squared. Okay. Now you look at this one. We want to complete the square, which means, right? We want to put this one as a form of a square of something. Okay. So we have this cross term X times U. But here we have R, so we have X times U R at PB. We have 2, so therefore, which means we just add an extra term, pbx squared, right? I have to put a pbx squared. Here we have 2 pbx times ru. I have ru squared. In this way, we can complete the square for this one. Because we add this one, of course, we have to subtract this one, make them equal to each other. So that's what we mean by complete the square. I put this one into a form of square of something. Because once we put it into a form of square of something, we know whether it's positive or negative, right? Okay, so here, that will be the square of pbx plus ru. That is this term, right? Square, and then we just copy the other 3 terms. Now you can look at this expression. Every term are in terms of square of something, right? That's what we call, what do we mean by complete the square? Huh? We want to put it into a form of square of something, not something times x times u. That's not what we want, right? This is what do we call complete the square. Okay, any questions? Okay, and then we put, so those 3 terms are all related to x squared, right? We put them together. So essentially we have x squared times something. Those one, you can those terms, they just depends upon p. We can design p, right? And then those qr are given, p, qr are given. So this one, this is another term for the square. That's what we do, how we did the complete the square, right? To take care of x times u. Then we put it back into the expression for the change rate of the Lyapunov function. Okay, now let's move on. So we haven't put any condition on p except we know that, okay, p has to be positive. Okay, in order to make this one, the change rate of v to be negative, right, or equal to 0, let's first make the first term here on the right hand side to be 0, which means that we want p satisfy this equation. Okay, this is a quadratic equation, right? You can easily, and we know q and r are all positive. You can easily verify that one root is positive and the other root will be negative for this equation. Okay, then we just pick the positive root for p, because one is positive, other one is negative, right? Only one solution will satisfy the requirement p is positive. Okay, so let's say we find out that p are to satisfy this, then this whole term will be 0. This is what's left in the expression of the change rate of v. Okay, any questions? So now we say we design that p to take care of one term. Now let's move on. After this one, we say the change rate of this v. Here we have those terms are related to the cost function. So now we just take let's just do the integration. We integrate both sides over t from 0 to infinity. And so what happens? So both sides, right, they do the integration from 0 to infinity. Okay, and this one on the left side, of course, we say because this one is the change rate of v, we do the integral. That becomes, right, just let's plug in the expression of this Lyapunov function, right? It's just px squared at infinity minus px squared at 0. On the right side, here you look at this one, qx squared plus ru squared. The integral of that, because we define this cost function j, right, is the 1/2 of this one. So this one is just 2 times j. Is that clear? Now we still just copy this one. We copy this one here. Okay. Now, on the left side, let's assume that the system is stable. Of course, you say, hey, how do you know? But okay, let's just assume this is the case. Later, we're going to prove that. But anyway, let's assume x system stable means that x will be 0 when time goes to infinity, right? So this one, x infinity will be 0. So finally, right, this one will be 0. So we will just put this j on the left side, x squared on the right side. So we get the expression of this cost function. The cost function will depend upon the initial condition. And the p is already fixed, right? We let a p satisfy our equation, right? We get a solution for that. So then we say, okay, this is a positive term. And then we have this integral. But if you look at this integral, the integrand, right, inside this integral, this is a positive term. So those whole thing, every term will be a positive. So if you sum them up, this one will be positive, right? So therefore, we know this cost function has a absolute minimum. The minimum depends upon the x squared at time t equals 0. Okay, but the question is, can we design our input to make the second term to be 0? Can we do that? So you just look at the expression. If we can make this one to be 0, right? Is that clear? So let's just try to. We want this one to be 0 to reach the minimum. You can say, hey, it's easy, right? I put the pbx plus ru equals 0. Then we get we solve for that, we get our control input. It is a, if you look at this form, when we solve this equation, then we get the u is just minus pb over r. So the scale is just pb over r. So we have solved the problem, right? So the whole idea, this procedure shows that the near-proof method will be the way to go to get the solution for the general case. Okay, but of course this is, but I only show you to get the solution for the scalar case, right? Then I'm going to show you how to do it for the general case. Okay, let's take a break. A 15 minutes break, then we'll talk about the solution for the general case. All right, okay, so let's Let's start the second half. So now we are going to extend the idea of the CDF method to deal with the general case. So we have this equation now. Remember x and u as vectors. We want to minimize this cost function. And then we will follow the DRF method again. In the scalar case, we design the DRF function as px squared. Now we want to convert this into the vector case. So what will it look like in the general case? What will be? Don't have x squared, right? X squared becomes x transpose times x. But then you have this p. That p will be appears in the middle. That is the positive definite matrix, right? Okay. So you have learned this in part 1, right? The Lyapunov function. Okay. Now, of course, we are going to design, right? We are going to design the P. But of course, we know the first requirement is that P is positive definite. Then let's try to get the change rate, right? We want to evaluate the change rate. We want to make the change rate to be non-positive. So therefore, let's just compute the derivative of this Lyapunov function with respect to time. This one is easier. You have done that. We have done that in part 1. So here, of course, this one is just the multiplication rule in calculus, right? You do the derivative, take the derivative one by one, right? The multiplication rule. Okay, put it in. We know the expression for the x dot, right? Let's put it in. And then we will get this one. So this one, x dot, right? You have to do the transpose. That's how this is the x dot transpose. When you do the transpose, of course, you have to change the sequence of the multiplication. Then this is the x dot, right? So we put the different terms together. We have two terms associated with x transpose x, right? A transpose p plus p times a. And then we have those cross terms, x u times x, right? Okay. Now, just to simplify, this one, those two terms are actually the same. Remember, because it is scalar, right? It is a scalar. The whole expression is scalar, so I can take a transpose of this expression. A transpose of this term is exactly this term, right? You get a transpose of this, you get x transpose times p transpose times b times u, but p transpose equals p. P is symmetric, positive definite. So that's why I just put those two together as 2 times x transpose p b u. Is that clear? Okay. Just like in the scalar case, we force it marry with the cost function. So we say this change rate of this, right? I want to be it to be related to the cost function. I have to plus x transpose qx plus u transpose rx, ru minus those two. Okay. And then we have to deal with all those terms. We know the final two terms that are negative, right? Now remember, right? Now this is the time for you to remember how did we deal with this 2pbxu in the scalar case? What did we do? What was the technique we used? Completed the square. Very good. We have to complete the square. Okay. Okay. So today you are going to learn how do we do that how do we do that for the matrix and vectors? So we know, okay, we have to complete the square. We know, okay, let's first recall what do we mean by complete the square for the scalar case. That's what we are familiar with. So you say, I have something xu, axu plus bu square. I want to put into a form of a square of something, right? Plus x squared. So we have to define this, figure out what is alpha, what is beta, and probably there is some constant c. But eventually I want to convert, I write this form into a square of something plus square of another thing, right? That's the meaning of completed the square. This one, of course, you know, but this time I want to complete the square for the matrix quadratic form. So which means, right? Which means let's just you just relate. So we have this xu actually means we have this 2x transpose pbu, right? Then this u square means actually we have this u transpose r times u. So completed the square means, right, I want to put it into a quadratic form, right, of something. Quadratic form means the square of something, right? But this square, but here we have alpha x plus beta u. So it means here I have a phi x plus gamma times u. Okay, and then here I have a c, so we have something in the middle, omega. So, and then this gamma x squared, so I have to determine what is d. So it's a square of x times d. That is the meaning of complete the square for a quadratic form. Okay. Now the problem is, right? How are we going to find out phi, gamma, omega, and d? So you just take the problem I started saying. You say, okay, I already know, right? And then I just expand this, and then we know this one has to be equal to left side, right? We will try to find out some equation for those phi, gamma, omega, and d. So let's just expand this. Okay. Then let's just do it step by step. So we say this is a transpose of this thing, right? Of course, we do the transpose, that becomes, we do the transpose, we change the sequence, right? So we get x transpose times phi transpose plus u transpose gamma transpose. Okay, and then copy everything else, right? Okay, and then next step, right? You just expand this out. We get x transpose phi transpose times omega phi x. And then the x transpose phi transpose omega gamma u, right? And then this term u transpose gamma transpose omega phi x, and then u transpose gamma transpose omega gamma times u. Those are the four terms come from this one, and then we keep the final term. Okay. Now, so let's just group those things together. And this here, this we keep this one. But if we look at those two, right? Those two, they are the same as before, because this one, right? We just take, let's say I take it is a scalar, right? If I take a transpose of this, will be the same. So I take the transpose, so we'll get x transpose, phi transpose, gamma transpose, but gamma is a symmetric matrix. Okay, and then we have this omega is a symmetric matrix, and this gamma, right? Transpose. I take the transpose of that, right? Then I get the gamma. So those two are the same. Those two are the same. So I just put them together. I get 2x transpose by transpose omega gamma times u. Okay? And then I still have this u transpose, this term, right? It's like a u squared term, and then I have this x squared term here. Those are the expansion of this quadratic form, right? And then we know, okay, this is supposed to be equal to this one. So clearly, we know this is equal to this one, right? So clearly you can say, hey, let's just look at this term x. So we have R2, x transpose times u, or x transpose times u. So clearly we can say this one must be equal to this one, right? Okay. And then we say, how about u transpose times u? I have this one. So therefore, this R should correspond to those. We'll first get those two equations. Okay, is that clear? So we can say, okay, this one, right? Omega, the gamma transpose omega gamma equals R, and this one equals P times P. So this one here equals P times B. Okay. Of course, with those two equations with many solutions, then we just pick up the simplest one. We say we just put those omega times gamma equals identity matrix. That will simplify the expression. Okay. Then if this is identity matrix, we get those just the gamma transpose equals R. Then, okay, from this one, we get the gamma equals R transpose, but R is symmetric, right? R transpose equals R. So we get the expression of gamma. Those phi transpose equals PB, right? Because this one is identity matrix. Okay, then I get this one, phi equals B transpose P. Okay. Then this omega gamma equals 1, right? Identity matrix. So we get, but gamma is just the R. So we get omega equals the inverse of R. Okay, so this is where we are. And we already determined this omega, right? Omega equals R inverse, this gamma equals R, and phi, right? We already determined those two. Then finally, how about D? Okay, now you compare this expression with this one. We know, right, this term, because in this expression, there is no x transpose times x, right? So this term has to be 0. This term has to be 0. Then in this way, we get D, right? That's how we completed the square for this matrix quadratic form. So we express those x times u and u square in terms of this one. Okay. Okay, now we plug in the expression of phi and gamma. That will be the looks like a complicated form, right? But I just show you how we end up with this expression. It's just a completed square for the matrix and vectors, and then it's okay. Any questions? So when we try to complete a square, well, we will try to get those matrix, right? We just expand them out. We compare with the original one. Then we can get those possible solutions. All right, so this would be the complete. This is the original form. We complete the square, we get this one. And then we plug it in. So this will be the final form for the change rate of this V, the Lyapunov function. So essentially we say, okay, this one, because it's quadratic form, now every term is a quadratic form. Is X transpose times a matrix, right? Times X, and then this one, right, is something, right, depends upon the either a combination of X and U, right? But it's this transpose times this matrix times this vector. So it's another quadratic form. And those two are the negative numbers because Q and R, they are all positive. All right, now we move on to the next step. So just follow what we did for the scalar case, while we will first try to make the first term to be 0. First term on this right-hand side to be 0, which means I have to find out a P such that, right, this term, right, equals 0. I just, okay, this whole thing equals 0, right? I just rewrite this one equals 0 as this equation. Just A transpose P plus P times A plus Q equals PBR inverse B transpose times P. That looks like a very complicated equation. Remember, a P is a matrix, right? This is what we call the algebraic Riccati equation. In the scalar case, right, if you recall what we did for the scalar case, that actually corresponds to the scalar case. A transpose P plus P times A. In the scalar case, it's just 2PA, right? Because we know those two are the same if they are scalars. Okay, we have this Q, right? This one, right? Because if the scalars were P square, or B square, R inverse, right, will be the denominator. But of course, because now we are dealing with the matrix, so that's why if we convert this one into a matrix, it looks more complicated. But anyway, so that is the equation that this P has to satisfy. Okay? So this ARE or algebraic Riccati equation, that is the key to the solution of optimal control problem. So we assume that we can get a solution for this ARE. Okay? So we can find a solution to satisfy this one. Then this whole thing, right, this first term, which is the pair, there'll be 0. Okay? Any questions? Basically, we just follow what we did for the scalar case, right? But somehow, because the scalar becomes vector, right? Scalar becomes the matrix. There's something, more complication will be involved. So I just try to show those complications, but the overall idea keeps the same. So this term disappears. This is what we have now for the expression of the change rate of the Lyapunov function. Just like in the scalar case, right? Then we just do the integration, right? If we do the integration, the left-hand side, right? We do the integral of this left-hand side, because this is already a derivative, right? Just the integral of this one is just the value of this linear function at infinity minus the value of the linear function at 0. And we assume that the system is stable. Therefore, the value at infinity will be 0. We only have the value at 0. Okay? But this way, say, hey, how do we know it's stable? So we are going to show that later. For the time being, we assume this is true. Then, how about the right-hand side, right? If we take an integral of those two terms, so this is the first term, those are the second term, and we know the second term, right? This will not correspond to the cost function, right? Then we reorganize, right? We can express the cost function in terms of the linear function, and also there is an integral, right, of a quadratic form. On this quadratic form, we know R, right? R is a positive matrix, right? Positive definite matrix. And this one, right? This is a vector, and this one, those two vectors are the same. It's just one is the transpose of another, right? Because this is positive, this is quadratic form. Therefore, we know this whole thing is positive, because R is a positive definite matrix. If we look at this one, because this whole thing is positive, we know the integral of this one will be positive, right? And also, unless, right, if this whole thing is 0, then it has a minimum value of 0. Then now the question is, can we make this? Can we make this one to be 0? Then you design your controller, right? You design your controller properly. Then you say, okay, I just put this vector to be 0. Then this quadratic form will be 0, right? Is that clear? Now, so the input has to satisfy this equation. Then you can get the control law will be in this form. Now, if you look at the way we solve this problem, remember, right, we choose the input in this way such that the whole integral is 0, right? Because we know this whole this integral has a minimum value of 0, right? Then when we say, is the solution unique, means, is there any other possible way to make this integral to be 0? For example, which means can you define another controller which is can be a nonlinear function of x, and then you plug it in, make this to be 0. Is it possible? How to make this one This is a quadratic form, right? Quadratic form, let's say if I have something, okay. Let's say if this one, we say, I want to make this one to be 0, because this one is positive definite. The only possibility is to make x equal 0. If x is not 0, we know this one will be bigger than 0. Okay? So now, tell me, is there, except this one, is there any other solution to make this to be 0? There is no other solution, right? So that's why at the beginning I said the solution to this optimal linear quadratic regulation problem has to be a linear state feedback in this way, and there is only one solution. Okay? You cannot use a nonlinear controller or any other powerful controller or whatever, say AI controller, whatever controller is, but this is the only solution, okay, to minimize this cost function. Is that clear? Okay. Remember, for power placement problem, for the multiple input case, we know there are infinite number of solutions, okay? But for the quadratic or for the optimal control, while looking at the optimal controller, there is only one. There is only one solution. There is no multiple solutions. There are no other solutions to make the cost function to the minimum. Okay? That's the difference between the optimal control and the power placement. Okay? And also we show you the linear controller. You say, hey, the form is so simple, but that is the only controller which can minimize this cost function. So this is a beautiful result because we show that the state feedback controller is a natural result from this linear quadratic regression rather than assumption. At the beginning, we assume that it is this linear feedback, but now we show it has to be in this form. There is no other way to minimize this cost function. Okay? Any questions? Okay, so then let's state the theorem 1. We say, okay, consider the system x dot equals ax plus bu. So we have this cost function. Now we know, okay, R is a positive definite matrix, Q is semi-positive definite. We will write Q equals H transpose times H. So with some condition, we say if AB is controllable and AH observable, the optimal control minimizing this cost function is given by this state feedback control, and this gain is calculated by this one. But what is P? We say P is a symmetric positive definite matrix satisfy this algebraic-Riccati equation. But of course, there is one step we didn't show, right? We didn't prove. We didn't prove that there is a solution to this one. We didn't prove there is actually only one solution. Of course, the mathematicians have already proven that, but we don't have the time to prove that in the class. Okay, that will be more involved. So, but just have to believe me, right? This subject has been studied for a long time. Okay, so there is only one solution for P. All right. Now let's look at example. How to apply this method for the simple case, and then we will see what are the complications may arise. Here is a simple scalar case, but the system is unstable, open loop. Now this cost function, of course, right? This Q is 1, R is 1. Then we know, okay, this is the ARE, this equation. In this case, we know A is 1, B is 1, right? Q is 1, R is 1. So immediately we can write down A is 1, right? We have 2P, Q is 1. This one, everything is 1, but P squared, so minus P squared plus 1 equals 0. Okay, P is a scalar. In this case, you can find out two solutions, and we know one is positive, another one is negative, right? So which one to choose? P has to be positive. You say there is only one solution, huh? You will never end up with two positive solutions, okay? So we choose the positive one, that is 1 plus square root of 2. Okay, and then we say we already know R and B, so we just plug in the expression for the controller, right? R, B, P, because this is 1, 1, right? So minus 1 plus square root of 2. That one, you get the solution for this optimal control, okay? So now in this case, this Riccati equation looks pretty straightforward to solve this Riccati equation. Okay, now let's look at the second example, and then you will realize it is not so straightforward. Okay, here then we consider a second order system. So here, okay, this one, this alpha and alpha 0 and alpha 1, they're just the coefficients of the correct polynomial, right? This form is already a controllable canonical form. But we know the controllable canonical form will not help us for the ARE. But anyway, this is A, is a 2x2 matrix. This is B, is a unit vector, right? And then this is Q. Q is a matrix 2x2. R, we say, okay, there's only one input, so that will simplify. The solutions R is just a scalar. Then, because it is the A is a 2x2 matrix, right? So therefore P will be a 2x2 matrix. Now we know because we require that P is symmetric. So actually there are three numbers to determine. Those two are the same because it's a symmetric matrix, right? Okay, so how are we going to get those three numbers? Then what is a Riccati equation? This is algebraic Riccati equation. So let's just plug it in. So this is A transpose, right? This is P, this is P, this is A, this is Q, this is okay, because this R, right? R is a scalar, so I've just put it here. So this is the B, right? Is 0, 1, 0, 1, and then this is the P. But we know those are the quadratic terms there. Okay, and then from this equation, right, you can derive three equations. So you say, okay, why there are only three? There are supposed to be four. But remember, right, eventually the matrix is a symmetric matrix. So you only get three terms. There is another term will be the same as one of them. So we get three equations. There are three design parameters, P11, P22, and P12. But if you look at those equations, you can say they are quadratic equations, right? So there are multiple solutions. Okay, let's say the P12 has two solutions from this one, P12. You can solve for that. Quadratic has two solutions. Then from P12, you can get the solution for P22. P22 is here. And then there's P11. So I skip the details on how to get those solutions. Okay, I just write down the solution here, but then you can say there are multiple solutions. Okay, and then you have to pick one of them. Only one of them is positive definite. Then you get the final answer for this P. There is only one solution. You can say the expression of the solution is quite complicated, right? And also it involves, right, the previously you have to decide how to determine a matrix is positive definite. Okay, I will discuss that later in another lecture, okay? But anyway, let's move on. You can say, okay, once you get this, the final answer for this one, you can say the expression is quite complicated, right? So definitely is much more difficult than the power placement. And then it is also time consuming. So here, what is the most time consuming part? Is how we solve the ARE, right? How we solve the algebraic quadratic equation. But we are going to come back to this point later. Let's move on. So we say, okay, it can be solved. Probably the calculation may be kind of tedious. Okay, but let's talk about some other things. How to select those Q and R? We say at the beginning we said, okay, the Q are just the weights, right? Define the importance, relative importance on the state vectors and the input values. In the power placement, we design the reference model to meet the performance specification. From performance specification, directly then we can provide the desired poles. We have the algorithm for that. But for this LQR, do we need to provide the desired poles directly? For this whole computational procedure, right? There is never a place asking for the poles, right? Okay, so we don't know where the desired poles are. So what are the design parameters? The design parameters are the weighting matrix Q and R. So Q and R have to be designed carefully to strike a balance between the response speed and energy efficiency. Now, but the difficult part for this design is we don't have a formula, right, to relate the time domain requirement to Q and R. For power placement, we have the formula to relate the rise time, the settling time, the maximum overshoot to the distribution lateral frequency, right? And then the desired poles. But for LQR, unfortunately, we don't have that. Okay. Then the selection, so that's how we design. Then the selection will be usually made on the basis of experience together with simulation of the result for different trial values. So you need to do some experiment. You try different possible values, right? But those possible weights will come from your experience. There are some general guidelines to simplify the design. So usually we choose our Q and R to be diagonal, right? Although in theory we say Q and R are symmetric, positive definite. So those cross terms may be non-zero, okay? But in reality, right, because you want to design something that you want to visualize, you want to know the meaning of those parameters. So therefore, it is simpler. You design those Q and R as just a diagonal matrix, right? That directly reflecting the weights for different state variable and the input values. And also, you the better, right? to use the original state variables. Those state variables are the variables with physical meaning. Well, like you use the speed, you use the position, right? You don't use the transformed state variable. We know the state variable can be transformed into another state variable, but those transformed state variable may have no meaning, may have no physical meaning. So you don't want to do that, because if you use those state variables and then you put some weight vector on those, you don't know its physical meaning. That will make your design much more difficult. Okay. And generally speaking, right, the larger value of this Q, which means you put more weights, on the state variables, means that you want to make the state variables go to 0 as fast as possible. Okay, but we know you want it to be very fast. Then the control effort has to be higher, right? So there, what we call nothing for nothing. There is no free lunch. Okay, and then you want to save the energy, right? You put more emphasis on the magnitude of the input, which means you put a higher value for R. Then you may expect that the speed, right, will be smaller, but it will slow down the performance. Okay, slow down the response of the system. Now, as I mentioned, right, we need to show the stability. We haven't proved that yet, but let's try to show that. In the previous solution, right, when we do the integral, we assume that system is stable. Right, we say the state variable at time goes to infinity is 0. But now let's try to show that this is the case. So we have this system. We apply the optimal control, right? We use this controller, and then this is the closed loop system. We know P satisfies this algebraic Ricard equation. Now we want to prove that X will go to 0 when time goes to infinity. So here we take the theorem 2. We say if the triple ABH is controllable and observable, then the closed loop system using the optimal control, which minimizes the quadratic cost function, is asymptotically stable. But here, I want to when we say observable, we are not here. This observable means our AH is observable. Okay, you can see it does not refer to the original system, right? Original system, we say there's AC. Right, you have this observability matrix to check, but here, this observable means, right, we talk about those two matrices are A and H. This is for the purpose of stability. Of course, later you are going to understand that, but let's move on. So let's just use the Lyapunov function, right? We already defined that. Previously, we have already shown this. When we try to derive the solution for the optimal control, right? We already showed this. We already choose the P to satisfy this Ricard equation, right? This one is 0. And also we designed the optimal controller such that those two actually, right? This term is also 0. So overall, this is the change rate of the ER function. Then we say, yes, indeed, it is less than or equal to 0, right? But this inequality only assures that the change rate is less than or equal to 0. Okay? Is that enough to guarantee asymptotic stability? It is not enough, right? We have to show something else. We need to show that if x is not 0, this v dot will be strictly negative. Okay, then that will complete the proof. So this how to do that? This way. Let's take a closer look at this v dot. Okay, let's plug in the expression of this input. So u equals minus kx, let's plug it in. Then we get this one with just kx transpose r, kx. Like I mentioned, right, there's a negative, right? They are cancelled out. Minus times minus, so still plus. So this one, the dv dt is just minus x transpose qx. Now this u is kx transpose r kx. Now here is the place. We want to express those q in terms of h. That's the purpose for proving the stability. Okay. Then we plug in q, right? Is h transpose times h. So therefore, those two are so actually is the first term essentially is just a hx transpose, right? So if we consider hx as a vector, so it's just the transpose of hx times the vector itself is the inner product of a vector h times x, right? That's why we want to do it. We want to split those q in terms of h times h. Okay, then in this way, this first term can be expressed as a inner product of one vector. Okay. Then the second term of it still is just this a vector times this is a positive definite matrix times kx. Okay, now we need to show that this v, we know the v dot. We want to show, we already know that this v dot will be less than or equal to 0, but we also want to show if x is not 0, then it is decreasing, right? The v dot will be less than 0. Okay, now let's just prove it by contradiction. We assume that if x is not 0, okay, and also if for those x, it may make this change rate to be 0. If that happens, if the change rate to be 0, right? And for some non-zero x, what would that imply? Okay, now we look at this expression, which means, okay, this term, right, this whole term to be 0, right? The change rate to be 0. But if you look at those two terms, both term has to be 0, right? Because we know both term, because this one is just an inner product of a vector. It is always positive unless the vector is 0, right? And also the second term, because R is positive definite, so the vector has to be 0. Otherwise, it will be positive. So therefore, we have kx equals 0 and hx equals 0. Is that clear? Okay. All right. Now, then we say, okay, this is the equation for the system, right? We know if kx equals 0, so we have a system x that equals ax. And then this is its output, h times x. We say the output is 0 for this. We can call it a virtual system, right? Because like I mentioned, well, h is not corresponding to c, but just say this is a virtual system. There is some, we say ah is observable, we say okay, hx is the output, but the output is 0. For an observable system, if a system is observable and if the output is 0, how about its state variables? What will be the state variables? The state variables has to be 0, right? From if a system is observable, right? That's what you have learned, huh? So if the output is 0, then x must be 0 due to the observability. Okay? But of course, this one will have a contradiction. First, we assume that x is not 0, but because of its output, all the output are 0, we know that the state has to be 0, therefore we have a contradiction. Then we have proved that for non-zero x, the change rate has to be negative. Okay? So overall, we have shown, therefore the closed loop must be isotopically stable and the proof is complete. And the way we prove that is the proof by contradiction. Okay, that is one of the most important tricks in mathematics. Remember, right? If you are interested, remember how do you prove that square root of 2 is an irrational number, right? You prove a contradiction. You assume that is rational, it's impossible. So for all those difficult problems, right, the proof by contradiction is a very interesting technique to use. Okay, now let's go back to the pitch controller design.
Right down for runway 27, number 2, we have the traffic on file.
Hi, I'm Dave Pressey with St. Charles Flying Service on behalf of Expert Village.
We're going to talk about the way in which we move an airplane in flight. Unlike your earthbound vehicle, an airplane can move in all 3 dimensions. This is accomplished by moving the control surfaces to change the airplane's attitude. There are 3 axes about which an aircraft moves: pitch, roll, and yaw. Pitch is the up and down movement of the nose. We can adjust the pitch of an aircraft by moving the control yoke forward and backward. Pulling back and forth in such a way moves the elevator, the horizontal hinge surface on the tail. Move the control yoke forward to lower the nose. Move it backward to raise it. An upward movement of the elevator causes the tail to be deflected downward, thus lifting the nose. A downward movement of the elevator raises the tail, thus lowering the nose. Pilots refer to this up or down movement of the nose as changing the aircraft's pitch attitude.
You can say how the pilot, right, manipulated the plane. Basically, they change the control surface of the elevator. Okay, here, those are the state variables. Previously we showed that the open loop is unstable. Right now, let's design the LQR. So in this case, let's use R equals 1, Q in this form. You can see those QR we put only one value is non-zero, so it's semi-positive definite, right? Okay. R is just a simple one, R equals 1. Then we can get the P and then we can get the gain. This is the step response. Then we can say the rise time, the overshoot, and the settling time. Now it is stable, right? And also the rise time, settling time, and the all overshoot, the all satisfy the performance requirements. Okay. But of course, you may say, how did I choose, right? This one, that comes through a number of experiments. But of course, here I just finally show you the solution. In order to get those solutions, you have to do the simulation, okay? In your mini project, right, you are supposed to, use the Simulink to simulate the response. You try different values, and then you look at the step response, and then you design it. Now, finally, we know there is a problem, right? In this whole procedure, there is how do we solve this algebraic Ricard equation? If the order of the system is more than one, right? We say for a second order system, the calculation is much more involved. So it has multiple solutions. You have to select one of them to be the correct one. Okay, of course, the people also know that they want to develop a systematic way to do it. Unfortunately, they have found one. Okay, but this one, right? You don't have to select, right, a solution out of many solutions. There is this procedure for you to compute, but this procedure involves, right, the eigenvalue and eigenvectors. But of course, that one, if you have MATLAB, right, and then you have a numeric procedure to compute that easily. Okay, so this one we say the original system is nth order, right? We know that the dimension of the vector, state vector is n. Well, to solve this problem, we have to form a much bigger matrix. The original is n, but n matrix is A, but we have to form a matrix gamma with a dimension of 2n by 2n. Okay, and those are the entries for this matrix. Okay, it's a more complicated matrix. Well, but it can be shown that this matrix has n stable eigenvalues and also n unstable eigenvalues, right? But we are only interested in those n stable eigenvalues. So for each stable eigenvalue, you compute the corresponding eigenvector of that 2n by 2n matrix. Okay, you get those eigenvector, but we know this eigenvector is 2n dimensional, right? Because that matrix is 2n by 2n. The eigenvector is 2n dimensional. And also, both the stable eigenvalue, the stable eigenvalue may be complex numbers. So those eigenvector may also be complex value. Okay, that is fine. So you may get some complex values. Now you get this eigenvector, this 2n by 2n. Then you will partition those 2n dimensional vector into a upper half and the lower half. The upper mu, right? We call it mu I, ith eigenvector. That's an n-dimensional one. The mu is a lower half one, is also n-dimensional vector. Right? The total is 2n dimensional. We split in the middle, you have 2. Okay. Then it can be shown. Okay. If you're interested, you can find the details in my lecture notes that those eigenvectors are related to the P matrix. This P matrix, the P is the solution to the ARE. Okay, P times the upper eigenvector equals the lower eigenvector. It's kind of a miracle, right? But somehow people developed this, okay, because of this, and then you have how many eigenvectors? You have n eigenvectors, right? Then you put them together. So we say P times V1 equals V1, right? P times V2 equals V2. So you put those V1, V2, Vn. This will be a n by n matrix because V are the n-dimensional vector. You put those n vectors together, right? To form a matrix. This P times each individual V, right, correspond to this mu, the lower half of the eigenvectors. You have mu1, mu2, mun. This is another matrix. So this is a matrix. This is another matrix. Now you can solve the P because those V1, they are the eigenvectors for different eigenvalues. Definitely they will be independent, right? Then you will say, okay, just get the inverse of this matrix. And then you multiply both sides, then you get the solution of this P. You can say from this one, right? The advantage is that, right, there is a well-formed computational procedure to follow, and there is only one solution. And we know in theory, there is only one solution. Okay? But normally, if you do it this way, right? Normally, you need to have some programming to help you. Either use MATLAB or other programming which can give you the eigenvector and eigenvalues. Because, right, if you have a let's say you have a second order system, then we know that matrix will be 2 times n, will be 4 by 4 matrix, right? You get the eigenvalue and eigenvector of 4 by 4 matrix, right? If you do it by hand, right, it is time consuming. Let alone, right, 3 by 3, then it's hopeless, right? We're not required to do that, right? 3 by 3 and then 6 by 6. No. But anyway, but let's say if you have MATLAB help you, right, this one should be a very easy for MATLAB. Okay. You get this P and then you can get the solution. Now, finally, let's compare these two ways to get the solution. Okay. This, because we want to do it by hand, so therefore let's make it simple. Let's make it simple. It's a first order system. So this A is -3, right? B is 1, this Q is 1, R is 1. Right, and then let's write down the Ricard equation. So this would be the Ricard equation. For this one, right, you can just directly solve the Ricard equation. It's a quadratic equation. You have two solutions. You know, one is positive, the other one will be negative. Because the positive one is square root of 10 minus 3. So don't worry, you always have a positive solution, okay? It's guaranteed. It will not happen, you end up with two positive solutions, or you happen with two negative solutions. It will never happen. It's guaranteed. You will have only one solution. Satisfy this Ricard equation. So therefore, you solve this quadratic equation, you get this P. Now let's follow the second way. We do the eigenvector way, right? So that one, we form the gamma matrix The original one is 1, so therefore will be 2 by 2 matrix. Okay, you put in the values of this A, B. A is -3, B is 1, right? So that's why we have -1. Q is 1, we have -1. Okay, so you have a matrix. Okay, this one, because it's a 2 by 2 matrix, you can compute its eigenvalues. The eigenvalues are square root of 10 plus and minus. Okay, and then you try to get the eigenvector correspond to the stable eigenvalue, be minus square root of 10. Okay, of course, you know, you may wonder why you say, hey, the eigenvector may be multiple 1, right? It's not just one solution. I can put a scalar, right? I can put a scalar to this. I can put a scalar factor that will always be the eigenvector, but that scalar factor will not affect the solution. Okay, so in reality, right? In reality, you just pick one simple form of the eigenvector, which will simplify your calculation. So here, just pick the simple one is that you put one value as 1, the other you get the other value. But if you use some other form, it does not affect the final solution. Okay, because the final solution in this way, right? P is just mu times the inverse of V, but V is just one number. Right? Like I said, if you put it multiply those two by same factor, it will not affect the solution. The final solution for the P will be the same as the previous one. Okay? Any questions on how we solve the Ricardo equation using 2 different ways? Okay? Now let's summarize what we have learned while we give you the solution for the linear quadratic regulator. We want to achieve a trade-off between the speed and the cost. So we'll give you the reasons. We discuss the conditions for solving the linear quadratic regulator problem. What are the conditions, right? The system has to be controllable. That is the same condition for the pole placement. Now, then we'll talk about when we formulate the cost function, we have to be careful about those Q and R, right? We have to put them into a proper form. We design those Q such that, right, the system is observable, okay? Which means that you have to put some state variables inside the performance index. Then, of course, all the state variable, all the input variables have to be inside the cost function. If you don't do that, some of the input may blow up. Then I give you the 2 methods for solving the ARE, right? You can directly, solve the Ricardo equation. Okay? That one, we know you may encounter some complicated issues when the order is high. So when the order of the system is low, you can directly solve it. When the order of the system is high, you will have to use the other way, use the eigenvector method. Then we prove the stability, right, of the optimal control system, right? Okay. Now, the final question I want to ask you, right? This whole process, I give you the solution to the LQR. When we try to derive the solution or try to derive the equation for the algebraic Ricardo equation, what is the key technique we use? Last week, we said the key technique is the controllable kinetic form. Today's lecture, what was the key technique you have learned? Completed the square, right? Completed the square for this matrix. So use the Lyakov method and complete the square for matrix quadratic form. That is something I want you to know to solve the LQR problem. Okay, so that is all for today. We'll see you next week. Thank you. How do we know that for minus lambda, then it's